right, so let's take a look at our second lesson on linear programming. We learned the nuts and bolts of how to do a linear programming problem in the last lesson. Here we're going to actually open up that process, and we're going to be looking at word problems, and we're going to be translating the word problems into those linear programming pieces that we looked at in the previous lesson. So I love steps, so I just wrote out some steps for us to take a look at. And this is, I think, very helpful just to kind of lay out how are we going to start? Well, the first thing that we would do is we would define the variables. And since we're going to be graphing these, it would really be, we need two variables. And we should really use x and y as our variables since we're going to be graphing. Now, do you have to use x and y? Well, no. But it just would be easier if you put them in terms of x and y. The second thing, or you don't have to do it exactly second, but we do need to write the objective quantity equation. This is what we're maximizing or minimizing. Okay, so that's what the objective quantity equation is. Then write the system of constraints. So these are the inequalities. We need to write a system of inequalities. Then we need to graph them. Okay, so we need to graph. Then we need to list the vertices like we did in that last lesson, the feasible region. Remember in the last one where the graph looks something kind of like this? Remember the feasible region, we had like the points of intersection was in here? That's called a feasible region. And we're looking at the vertices. Remember on that last one we had 4 vertices to look at. So we would list the vertices of the feasible region, and then we would plug those vertices into our objective quantity equation to find the minimum and maximum value, whichever one we're asked to do. Maybe we're asked to both, or maybe one or the other. So those are the steps that we're going to take in this next problem, in this one problem that we're going to do. Okay, so we have officers of a high school senior class are planning to rent buses and vans for a class trip. Buses and vans. Okay, each bus can transport 40 students, requires 3 chaperones, and costs $1,200 to rent. Each van can transport 8 students, requires 1 chaperone, and costs $100 to rent. Look at what they're talking about. Everything that they are referring to either has to do with the bus or it has to do with the van. Okay, so our first step is to assign variables. Does it matter which is x and which is y? No, we just really should write it down so we know. I made x the number of buses, and I made y the number of vans. Okay, step 1 done. We've identified our variables. Okay, let's see. There are 400 students in the senior class that could be eligible to go. The officers have to accommodate at least 400. Since only 36 parents have volunteered to serve as chaperones, they can use at most 36 chaperones. All right. How many vehicles of each type should the officers rent in order to minimize, oh, look at there, there's that word, minimize the transportation costs? Okay, minimize the transportation costs. Let's do our objective quantity step next. So the cost, what would the cost be? Let's see. The cost would be $1,200 to rent a bus. $1,200 times the number of buses plus, let's see, $100 to rent a van. Okay, so there's our equation for objective. That's what we're going to use to maximize or minimize. Let's see. So now our job is to, let's kind of look back up here and remind ourselves. So we have defined our variables, check. We've written the objective quantity equation, check. Now we need to write the system of constraints and then just graph and go. Let's see. So the bus, let's see how many students. We've got 400 students we need to account for. So let's talk about a numbers equation first. So these are numbers of students. So how are we going to accommodate the numbers of students? Let's see. So buses can take 40 students. So this is going to be our list. So we've got 40 students in the bus plus, let's see, vans take 8 students. And I mean, that's all we have, right? The 400, that quantity, whatever 40x plus 8y has to be, 400 has to be the, let's see, 400 has to be the biggest number, right? That has to be smaller, the 400. Okay. Very good. So whatever that is, that combination has to be less than or equal to 400. It can't be more than 400 students because they are only 400 students. So that's a numbers equation. Let's see, what else do we have? We have chaperones. That's a deal, right? A big deal. So we only have, the most chaperones we have are 36. Let's see, how many chaperones? So a bus needs 3 chaperones. So 3x plus, let's see, a van needs 1 chaperone. And I can only have 36. That number has to be smaller than or equal to 36. Now, those two equations are kind of tricky to get. They're probably the harder inequalities, actually, not equations, inequalities to get. But there are some that seem like common sense, but students many times forget to write them down. And so that has to typically do with the variable itself, the number of buses. So x can't be negative, right? We can't have a negative number of buses. So x has to be greater than or equal to 0, because that's what would make sense. And the vans, we can't have negative vans, so y has to be greater than or equal to 0. That's why on this graph over here you can see we are in the first quadrant only. All right, so we have our the first steps done. Now we just need to graph and figure out where the feasible region is. Okay. In this case, these inequalities are not set up to graph very easily. Now this one would be pretty quick to do. I'm just going to move the 3x over, so y is going to be less than or equal to negative 3x plus 36. Wow, 36, there aren't 36 here. We're going to have to do some figuring out how we're going to scale this. Okay, on this one, so let's work on this one in a different color. This one we'll make green. So we've got 8y is less than or equal to negative 40x plus 400. Dividing everything by 8, y is less than or equal to, let's see, 40 divided by 8 would be what, a negative 5x, and 400 divided by 8 is what, 50. So I need a scale that would reach 50. Okay, so let's see, what did I do? What I did is I went by 2s. So let's do the scale in different colors. So 2, 4, 6, 8, 10. 2, 4, 6, 8, 20. 2, 4, 6, 8, 30. Now, do you have to do exactly what I've done? Oh, absolutely not. You can do a different scale if you want to. 2, 4, 6, 8, 40. And then 2, 4, 6, 8, 50. we'll do 50 is up here. Oops. Okay. So there's 50. So let's do the green one first. Let's see, the y-intercept is at 50. Right here. Now, these are in 2s, so why don't we take this slope and make it -10/2, right? So that'll be easier for us to count. So we're going to go down 10 and over 2. Down 10 and over 2. Remember, this scale is the same. 2, 4, 6, 8, 10. 2, 4, 6, 8, 20. 2, 4, 6, 8, 30. Okay, so let's draw that. Let's use green. Okay. Okay, so now let's look at the other one. Um, 36, 32, 4. So it'll be right here. And then 3, we'll make that slope 6/2, so we can go down 6 over 2. 2, 4, 6, 2. 2, 4, 6, 2. Okay. See if we can catch that. Okay. And then we have our x is greater than or equal to 0 and y is greater than or equal to 0. So basically we're just looking at, and just for fun, we'll just put this in pink. Why not? Come on, little ruler, you can do it. There we go. Okay. Looks like this is our, let's make this a little bit bigger. Looks like this is our feasible region. Right in here. All right, so let's outline our vertices. We've got this one, and we've got these two down here. Okay. All right, so let's list those vertices. We've got, we'll call this one number 1, and this one number 2, and that one number 3. Okay, so our vertices. The first one is 10, 0. The second one is 12, 0. The third one, it's kind of hard to tell. So just to be on the safe side, let's go ahead and intersect the blue and the green one, right? The light blue and the green, because that's where that number 3 is where they cross. So we'd have negative 3x plus 36 equals negative 5x plus 50. All right, so let's move the 5x over, move the 36 over. So x is 7. To get my y value, I would just plug that 7 into either of the blue or the light blue or the green line. Doesn't really matter. I'm going to pick the light blue one. So y would be negative 3 times 7 plus 36. So y would be, what, 15. Okay. Now you remember from the last example, our next step is just to plug those into the objective quantity. So let's do that. So we have C of 10, 0 is going to be 1200 times 10 plus 100 times 0. And that would give us 12,000. So if we did 10 buses and 0 vans, it would cost $12,000. So C of 12, 0 would give us 1,200 times 10, times 12, plus 100 times 0, which would be 1,440. Well, 14,400. Oh, that's not a better cost. The last one is 715, so we would do 7 buses and 15 vans, and that would cost 9,900. Ah, that's the lowest cost. So our answer is going to be 7 buses and 15 vans for a total of $9,900. Let's see what the question asks. It says, how many of each type and what are the transportation costs? Yay, so we got the type and the cost right here. All right, great.